In this video, we're going to take a look at adding and subtracting vector quantities. To start with the show, I need to explain exactly what I mean when I say a vector or a scalar value. A vector or a scalar is any quantity in physics that does not have a direction associated with it, so it's a magnitude only. Recall that when I talk about magnitude, magnitude is just a numerical value with units. A vector is any quantity in physics that has both a magnitude and a direction. So a scalar value is just a magnitude, meaning it has a numerical value in a unit, and a vector value has both a numerical unit, a numerical value, as well as a direction associated with it. The one thing that we want to really focus on in this lesson about vectors is how to graphically represent them. And when we graphically represent vectors, we represent them as an arrow. The length of the arrow represents magnitude, and the direction that the arrow points in shows the direction that the vector is pointing in. There must be some scale that represents that we can use to interpret how much a length of a vector would represent, and there needs to be some sort of coordinate system that so we could represent our graphical representation of our vectors to whatever's happening in real life. So let's talk about what our coordinate systems can be. There's a couple different ones. The most common one that we're used to is either the Cartesian coordinate system, that is x and y, or the cardinal coordinate system. This is north, south, east, and west. And these two coordinate systems are the ones that we're going to use in physics. Whenever you have a direction of some vector that's not lying on a pure direction, so it's not purely east or it's not purely north, but maybe the direction is somewhere between east and north, you have to give the direction as an angle off of some known coordinate system or some known axis within the coordinate system. We'll get to that in a minute. Let's first talk about adding vectors together. When we add vectors graphically together, we're going to use the tip-to-tail method in this class. And when we add these vectors together, the sum of our vector additions can be referred to as the resultant vector. And the vectors that we add together to get the resultant vector are going to be referred to as component vectors. So we have resultant vectors, which is the sum, and then component vectors, which are the things we add up to get to the sum. And this tip-to-tail method has a certain procedure. Before you even start the tip-to-tail method, the first thing you have to do is you have to pick an appropriate scale in order to graphically represent the magnitudes. Once you have that appropriate scale, you can use a ruler and a protractor to draw the vectors in the appropriate directions based on what the problem's giving you, and then you would label these vectors. When you go to add your second vector to your first vector, so you've graphically represented your first vector, you'll start your second vector at the head or the tip of your first vector. This is the tip-to-tail method. So you start your vectors at their tail, and you start your second vector at the tip of your first one. And when I show you some examples of this, this will make more sense. When you get to the end of it, after you've drawn all your vectors tip to tail as you go through, ultimately you're going to have your first vector still with an open tail, and then your last vector is going to end in a tip. So you draw your resultant vector from the tail of your first vector to the tip of your last vector. This is how we find our resultant. So all the things you add together are the components, and the resultant is just from the tail of the first to the tip of the last. Once you have your vector resultant drawn, you can use the tip-to-tail method in order to find the magnitude of this vector. All you have to do is measure the length of the vector, and then the scale that you use in your vector diagram could be used again to interpret this vector and give it a real-life value. After you get the magnitude, you can then, based on what you see in your vector diagram, identify the direction, either using an angle or not. So let's go through, and I'm going to show you a couple of examples and work through a couple of vector problems so we can see how this plays out. In this first example, we have a man who walks 54.5 meters east. So here we have a vector in blue showing this direction eastward, which is to the right. Then this man walks another 30 meters to the east, this time in red. If we're adding these, you'll see that I put the second vector, the tail of the red vector, at the tip of the blue vector. This is the tip-to-tail method. We add these together, and down below in purple, you can see the vector resultant. It's from the tail of the first to the tip of the last, and this would be 84.5 meters to the east. Whenever you have the magnitude, you have to make sure your magnitude and your direction always point in the right way, and your magnitude by the arrow length is always appropriate. And if you have two vectors that are pointing in the same direction, they're going to share the same sign, you end up adding them together. On the flip side of that is subtraction of vectors. In this scenario, we have a man that's walking 54.5 meters east, same as before, but now instead of walking further east, this individual is going to walk to the west. Now you'll see that I start the tail of my red vector at the tip of my blue vector. So I'm using the tip to tail method. And now I'm going to draw my resultant vector from the tail of my first to the tip of my last. And I've displaced it a little bit down below so you can see better. But you can see the magnitude of it and the direction gives us 24.5 meters, and that's east. So when you have two vectors going in opposite direction, the magnitude is always determined by subtracting their magnitudes. Now this explains everything in one dimension, but one thing we haven't done in class and that we want to do for the first time here is talk about how we establish two-dimensional vectors. In this scenario, we're going to use the Pythagorean theorem. So why don't we take this man, he's going to walk 95 kilometers eastwards and then 55 kilometers northwards. If we want to find out the resultant displacement of this individual, we're just going to determine the magnitude of it. So here we have 95 kilometers east as a vector, and now we have 55 kilometers north. And you can see by our scale that we have in the top right that we're pointing our vector directions in the right way based on our scale. The man started at the tail of the first, and he ended at the tip of the last. So our resultant vector is going to go from the tail of the first to the tip of the last, and what we've made is a right triangle. Whenever you have perpendicular vector components that you add together, your resultant vector is always going to be some right triangle resultant hypotenuse. The legs of the right triangle are your vector components. So you have your eastward component, that's the 95 kilometers, and you have your northward component by your 55 kilometers. So whenever you're looking at adding vectors and they're perpendicular, your components become the legs of the right triangle, and your hypotenuse becomes the resultant of the right triangle. Once you have that, you could just use Pythagorean's theorem in order to determine what the resultant is, using a squared plus b squared equals c squared. And here you can see the math on the right where I've done that. The last thing we want to talk about is this individual walked 109 kilometers, but we haven't given this person a direction yet. All we've done is given the magnitude of the resultant displacement. But we can go a step further and give them a direction as well. Now this direction is not lying across the east or the northern direction. It's given as an angle between the eastward direction and the northward. Now we're measuring the angle from the eastward direction, so we call that north of east, identifying that the angle is measured to some vector that is northward measured from east, hence north of east. And we're going to find exactly what this vector direction is. So if I reimpose this, we had a 95 kilometer eastward motion, a 55 kilometer northward motion. Ultimately, we found through Pythagorean's theorem that this motion displacement was 109.8 kilometers. We want to find now the angle north of east that the individual is running or moving. So here we take the arctangent. The tan theta is equal to the opposite side divided by the adjacent side. That would be 55 kilometers divided by 95 kilometers, gives us 0.5789. So tan theta is equal to 0.5789. If you do the inverse tangent to both sides, you end up with a degrees of 30 degrees. So we can say as a total for this direction, the person's walking 109.8 kilometers, right? And they're walking at an angle of 30 degrees north of east. This tells you a displacement, this tells you a direction, and it gives it both on our scales. One thing that I want to talk about, just to finish this, is I want to talk about vector components. So far we've looked at having a component, and then we've gone to a vector, but we can actually go the opposite way. We can take vectors that are given in two dimensions, right, that already have a northward and eastward component, and we can resolve these into their perpendicular components. in sense, we're now, instead of going from the two legs of the right triangle to the hypotenuse, we're going to go the other way, and we're going to have the hypotenuse to the right triangle, and we're going to resolve it into the two leg components. So here I've shown you just the right triangle. We're going to be starting with vector A, and that's just a generic vector, and we're going to find out what the components are in the two perpendicular sides. And we're going to do that with this example. In this example, a student is running with a velocity of 12 meters per second at an angle of 25 degrees north of east. And you can see this in the vector diagram down below. And what I want to find out is what's the components of her motion in the eastward and northward directions. So to do that, I'm going to use my sine and cosine functions. And the first thing I'm going to do is I'm going to say that my sine theta, which is equal to opposite over hypotenuse. And my opposite here is going to be this one, and this is going to be my velocity in the northward direction. And you can see that based on our scale, north is pointing up, this component is pointing up, it's opposite of my 25 degrees. So I can rewrite this substituting in my values. I have sine of 25 degrees is equal to the velocity I'm trying to solve for, northwards, divided by my hypotenuse velocity, which is 12 meters per second. This ultimately will give me a velocity northwards. If I take sine of 25 and multiply it by 12, I end up with 5.1 meters per second. And this is the amount that this individual is moving northward every second. So every second, this individual displaces 5.1 meters every second. So I'll write that on the diagram, 5.1 meters per second. Now I'm going to find out what the other component is. And to do this one, I'm going to use cosine theta, and that's equal to my adjacent divided by my hypotenuse. Now my adjacent value here is going to be my velocity component eastward. So rewriting this, I'm going to say cosine of 25 degrees is equal to my velocity eastward divided by my hypotenuse, which is 12 meters per second. And if I take cosine of 25 and I multiply it by 12, I end up with the velocity eastward equal to 10.9 meters per second. Now, I can represent this vector in two ways. I can say that the individual is moving 12 meters per second at 25 degrees north of east, but I could also say that the individual is simultaneously moving 10.9 meters eastward while at the same time moving 5.1 meters per second northward. Those two, the components themselves or the resultant vector, are mathematically equivalent. In the next couple of slides, I'm going to have you do some practice problems, just trying some of these vector components, and then there's a form at the end that I'd like you to try. And if you have any other questions, just please send me an email.